Welcome back everyone. In this lecture we are going to see some identities involving binomial coefficients. So, let us start with recalling what are the binomial coefficients. So, we have for any n and k non-negative integers such that n is greater than or equal to k, we have this n choose k which counts the number of k subsets of this given n set. So, that is given very explicitly as n factorial divided by k factorial times n minus k factorial. So, this is the very explicit form of the binomial coefficients. So, for n greater than or equal to k, we can take this to be the definition, and whenever n is less than k, we can define this to be 0. So, for n is less than k, we define by convention that n choose k is 0. And there are many important identities that one can prove among these binomial coefficients, and it will be very difficult to actually list even the identities that are actually identities that involving these binomial coefficients. So, what I am going to do in this lecture, I am going to actually introduce this Pascal matrix, and then we are going to actually prove some important identities that actually comes out of counting in two ways from Pascal matrix. Okay, so let us actually start with something simpler. First, we will actually see there is this basic identity among these binomial coefficients. We have already seen proof of this using counting in two ways, and one can actually directly apply the formula that I have written here and then prove the same identity. That the very first identity that we see that is the following. So, when we take this n choose k, which is same as n choose n minus k, and like I said, it can be proved using counting in two ways. For example, the left hand side counts that number of k subsets of I n. Recall that I n is given by 1 to n, and similarly the second the right hand side, it counts number of n minus k subsets of I n, and they count the same thing because we can actually define this bijection from this k subsets of I n to n minus k subsets of I n as follows. You take a k subset A and then send it to its complement I n difference A, and if this is k subset, then it is clear that this the complement will be exactly n minus k subset, and this gives a bijection. And now, this bijection establishes that this equality must be true, and this can be directly checked using this formula. So, that maybe I will leave it to you to check. And now, the second identity that we are going to see among these binomial coefficients is the Pascal recurrence. The Pascal recurrence also can be proved. I already proved, I guess, using this counting two ways arguments, but anyway one can also use directly the formula that is written here in the first slide to prove the same Pascal recurrence. The Pascal recurrence says that if you take this n choose k, which is exactly equal to n minus 1 choose k minus 1 plus n minus 1 choose k. So, this formula is true, and one can actually assuming that n choose k is 0 for whenever n is less than k. So, this equality is going to hold for all n k greater than or equal to 0 for all non-negative integers. So, this equality is true. and with the convention that n choose 0 is exactly 1. Okay. And this is what we call it as Pascal recurrence. Pascal recurrence. Okay, now I am going to introduce Pascal matrix and using this matrix we will be able to prove many more identities among these binomial coefficients. So, let us introduce this the Pascal matrix consisting of all these binomial coefficients as its entries. So, more precisely, so Pascal matrix is defined for given n. So, fix n coming from natural numbers. So, n is a positive integer. So, then you take this matrix P n which is defined to be whose entries are just the binomial coefficients n choose k. So, basically it is an n plus 1 by n plus 1 matrix and n actually the row index and k is the column index. So, okay, this is I am not fixing n maybe. So, it is clear that what is the matrix. So, the matrix is given by just the n kth entry is given by n choose k. So, n denotes the row index and k is the column index. Okay, so let us look at some example when n equal to 3. So, we get something like this. So, we have this matrix which is 4 by 4 and we are recording like n varies up to 3. Okay. So, it is 0, 1, 2, 3 and here k varies 0, 1, 2, 3. So, now the entries are given by n choose k. Okay. Then that means this is indeed an n plus 1 by n plus 1 matrix. So, now okay, given this we will just fill the entries. So, when n varies and k varies we want to just take n choose k as the matrix entries. So, we can see that when n is 0 then except 0 choose 0 all other entries will be 0 and similarly when k is 0 all the entries will be 1 and similarly the diagonal n choose n will be 1 and the lower triangular entries all the upper triangular strictly upper triangular entries are 0 and the lower triangular entries for example, this is 2 choose 1 and 3 choose 1 they are just 2 and 3 and 3 choose 2 is same as 3 choose 1. So, which is exactly 3. So, this is the matrix that we are getting. So, when we look at this Pascal matrix. So, now what we are going to do? We are going to actually focus on the entries of the Pascal matrix and then we will actually count in different ways. So, let us look at what happens to the entries. So, if we actually look at the total number of subsets of I n, so that is going to give us something like this. So, let us start proving some identities. So, let us look at the total number of subsets of I n. So, which we know that it is exactly given by 2 power n by counting in two different ways for given cardinality. So, we can count the number of subsets having cardinality k in I n. So, that is given by n choose k. So, then this n choose k. So, which is exactly is the number of k subsets of I n and if we count with respect to the cardinality then for k from 0 to n, this sum is going to give us all possible subsets of I n, which is 2 power n. So, this counting in two different ways tells us that 2 power n must be equal to some n choose k ranging from 0 to n. So, that means we have fixed n, and then we have taken the entries in the row, and then we have just summed all of them, then we are actually getting this 2 power n. So, for example, if we fix this 3, which is n equal to 3, so then we have taken this row which consisting of n choose k for various k, and then if you sum all the entries in this row, then you are getting exactly 2 power n, which is exactly 8 here, which is 2 power 3. Okay, so, this is what we are getting for the row sum, and similarly what we can do, we can also do this column sum of index k down to row n, and then we will see what we get. So, let us look at this, the column sum of index k down to row n, and this is going to be, so we have taken the index k. So, that means so it will start with this k choose k and then go all the way to n choose k. So, it will start with k choose k plus etcetera all the way to n choose k. So, this actually one can rewrite as follows. So, if we just to look at the column sum, this is same as you take from I ranging from 0 to n, okay. So, I have actually fixed k, and then looking at the column sum. So, if I fix, let us say fix k and then look at the column sum, then the n is varying. So, then what we are getting is just I choose k, where I is varying from 0 to n, and this is the column sum of index k down to n, row n, and which is same as this k choose k plus etcetera plus n choose k, because I choose k will be 0 whenever I is less than k. So, now what is this? One can actually prove that this is exactly equal to n plus 1 choose k plus 1. So, the claim is that when we take this summation I choose k, I ranging from 0 to n, which is exactly same as n plus 1 choose k plus 1. Okay, why this is true? So, let us closely look at all possible k plus 1 subsets of n plus 1, and then use the following bijection. So, let us take this subsets that has exactly cardinality k plus 1 inside I n plus 1. So, this is the set of subsets of I n plus 1 having k plus 1 elements. Okay. So, now if we take a set A from this collection and then just to remove I plus 1 from that. So, based on this I, so then what is this I? That I we choose it to be the max of A. So, look at max of A and then call it as I plus 1. So, then I plus 1 indeed runs over from 0 to n. Okay. So, that is the value it can take. So, now what we are going to do? We just take this A and then remove this I plus 1, and which is going to be a k subset, because this is actually k plus 1 subset of I n plus 1. So, now we have removed one element from this k plus 1 subset. So, what we are going to get is actually a k subset of I n plus 1 difference I plus 1, which is exactly n set. So, this is exactly n set, and this gives a bijection between k plus 1 subsets of I n plus 1 and k subsets of 1 to I. So, because this k subset of this I n plus 1 difference I plus 1 can be thought of as k subset of 1 to I. So, this is even though it belongs to here. So, we are going to make a remark that this A difference I plus 1 is indeed subset of 1 to I. Okay. So, let us make the things explicit. We have taken this k plus 1 subsets of this I n plus 1. From there, we are going to take this disjoint union of where I ranging from 0 to n, k subsets of 1 to I. Okay. The map is defined to be A goes to A difference I plus n, I plus 1, where the I is chosen to be I plus 1 equal to the max of A. Okay. And it is easy to see that this map is indeed a bijective correspondence. So, this is a bijection, and in particularly the cardinality of this I n plus 1 choose k plus 1 is going to be equal to the sum of the cardinality of k subsets of 1 to I. So, that means n plus 1 choose k plus 1 is exactly equal to the summation I ranging from 0 to n I choose k, and the column sum is exactly equal to this n plus 1 choose k plus 1. That is what we are getting. So, now we are going to actually do the counting on the down diagonal from left to right, starting with row m and column 0. So, let us look at what happens. So, the down diagonal from left to right, starting with row m and column 0. So, this is going to be exactly equal to the summation m plus I choose I, okay, where I is running over from 0 to n. And we want to actually prove that. So, this is exactly equal to m plus n plus 1 choose n. Okay, let us see how one can prove this. So, let us look at this sum, which is exactly given by summation m plus I choose I, where I is from 0 to m, which is using this first identity on this binomial coefficients n choose k is same as n choose n minus k. We can rewrite this as summation I range from 0 to. So, we are looking at the down diagonal from left to right, starting with row m and column 0. So, that means in the matrix, so it is going to look like. So, this is the column 0, and then you are starting with the row m. So, this is the entry, and then you are going to go all the way down here. So, this is the sum we are looking at. So, the entry should actually vary from I equal to 0 to n, because we are going to take m plus I choose I, So, that is the entry here, and then you go all the way the I ranging from 0 to n. So, this should be corrected. So, this term must be n. So, this is n. So, that means this is also n. So, then we can see that this term, which is summation I ranging from 0 to n, m plus I choose I is exactly equal to summation 0 to n m plus I choose m plus I minus I, which is exactly m plus I choose m. So, which is exactly equal to m plus I choose m, where I range from 0 to n. But this is same as saying that you take the summation k choose m, where k is running over 0 to m plus n. So, which is similar to what we have seen here. So, you take summation I choose k, I ranging from 0 to n, that is given by n plus 1 choose k plus 1. So, if we use that, then this is exactly equal to m plus n plus 1 choose n. Okay. So, that is what we are getting. So, we proved that summation m plus I choose I, where I ranging from 0 to n, which is the down diagonal from left to right, starting with the row m and column 0. So, that is exactly equal to m plus n plus 1 choose n. So, this is true. Okay. So, like this we will be able to prove many interesting identities. So, maybe I will leave some of them as exercise. So, prove that the following identity is again true. So, we can take this n choose m, and then you can multiply with m choose k. Now, if you use the formulas for n choose m, then you can prove that this is same as you can actually take n choose k, and then you multiply with n minus k choose m minus k, and this is true for all n m k greater than or equal to 1. Okay. And similarly, one can prove that when we take this alternating sum, so minus 1 power k n choose k, where k is varying from 0 to m. So, this is again equal to minus 1 power m n minus 1 choose m. Okay. So, when k actually varies from 0 to n, again we have formula. So, that is going to be 0, because n minus 1 choose n is 0. So, we get that for free from the second formula. So, these formulas, like I said, one can actually prove various identities for these binomial coefficients, and there are like books dedicated to them. So, one can actually check these things online and then see what are other identities one can prove using these counting arguments. Okay. So, let us move on. So, now I am going to actually state this binomial theorem. Maybe you are already familiar with this, but let us actually state and then prove it using combinatorics. So, here is the binomial theorem. So, I am going to actually take two commuting variables. I am going to call them as x and y. So, let us say x and y are given two commuting variables. So, that means we allow x y equal to y x. Okay, whenever you see some expressions or products involving x and y, you allow x and y to commute. That is the meaning of commuting variables. So, now if we look at the expansion of x plus y power n, and then that is given by this binomial theorem, which actually explicitly writes like using the count on how many x that can appear and y can appear. We can write it as follows: the x plus y power n for any natural number n, okay, for any n greater than or equal to 1, okay. One can actually take n to be any integer, not a problem, but anyway let us see only for n greater than or equal to, like we can take it to be 0. So, for n non-negative integer, so you have x plus y power n is being equal to summation k ranging from 0 to n choose k and then x power k y power n minus k. So, this is the identity that we have, and this identity is called binomial theorem, and one can generalize this identity for other variables. Then we will have binomial series. So, let us not talk about that right now. So, let us only focus on this binomial theorem, which only talks about expansion of this x plus y power n. Okay, so how one can actually prove this? I am going to actually prove this by spelling out the expansion x plus y power n. So, now if you think about it, recall that so when we are actually looking at this words that you can actually form using the alphabets 0 and 1, which have length n. Okay. So, this n words, so over this 0 comma 1. So, we proved that the number of n words which are exactly given by 2 power n. Okay. So, the word for example was looking like this: when n equal to 4, we have something like 0 1 0 0. So, this is a word, and similarly 1 1 0 0, and this is a word. And we also established a bijective correspondence between the n words over 0 comma 1 and the subsets of this n set I n. Okay. There is a bijection between this n words over 0 comma 1 and the subsets of I n. So, which is exactly the power set of I. And this bijection is what we are going to explore. So, if we actually instead of using x and y, if we use the symbols 0 comma 1, then what we are going to get on the left side is the following. So, you take 0 plus 1 and then rise it power n. So, then if we do it as like a formal way, so then you can see that this is going to give us, let us do for n equal to 2. So, then this is going to give us like 0 plus 1 times 0 plus 1, which is exactly equal to 0 0 plus 0 1 plus 1 0 plus 1 1. So, this is what we are going to get. So, now we know that the zeros corresponds to elements that are not there from this 1 to n, and 1 corresponds to the elements that are there from 1 to n. So, then based on the number of elements, if we start counting, the number of ones is going to count exactly the number of elements that is going to appear in that subsets. And with respect to that, if we actually start counting, so then we can see that n choose k is going to be the number of words that has exactly k number of x's in it. Okay. Or we can replace this as follows. So, we are going to count the number of words that has exactly k number of ones in it. It is going to be exactly equal to, so the ones will correspond to the subset that we are going to actually choose the elements that we are going to choose for that subset. So, because we have already labeled the elements to be 1 to n and given a n word from this over this 0 comma 1 is going to choose a subset from this 1 to n. So, because of that the number of words that has exactly k number of ones in it is going to be the number of k subsets of this I n, which is exactly given by n choose k. Okay. So, that means here this is something we can rewrite as summation all possible words. So, we take the words where this words actually comes from this 0 comma 1 power n. Okay. So, this is what we are going to have as a formal identity. So, now we can replace 0 by x and 1 by y or the vice versa. So, then we can expand, then what we get is actually the following. So, if we expand this x plus y power n, we exactly get the same thing. So, this is going to be the summation over all possible n words that we can actually form from x and y. So, this is like all n words where n words over this x and y. And now, what we are going to do? We are going to just count these words with respect to the number of x's that appear. So, then if you count this with the number of x's that can appear, the number of x's can be just from 0 to n. So, where this k counts the number of x's appear in the word. So, then using this you can see that, so the number of words that has exactly k number of x's is going to be n choose k, and since x has exactly k number of times it is appearing. So, it will have exponent x power k, and since y will be the rest of alphabets in the word. So, it will be exactly n minus k number of times it will appear. So, that tells us that this x plus y power n must be equal to the summation n choose k x power k times y power n minus k, and this is actually true for all n and k, sorry, all for all n non-negative integers, and this is what actually the binomial theorem says. So, I am going to leave this van der Waals identity as an exercise. So, one can also prove for x and y non-negative integers that if we take x plus y choose n, and I am using the variables x and y because this identity is also true at the level of variables, but we have not defined what is x choose k, but for x and y non-negative integers we know that what is x plus y choose n means, and using that you can see that this x plus y choose n is exactly given by k range from 0 to n, x choose k and then y choose n minus k. And this is true for all n greater than or equal to 1. Okay. And this is what called van der Waals identity, and I am going to leave it as exercise. One can prove this using induction. Okay, I will stop here and then I will continue with some other topics in the next class. Thank you. I will stop here.